In Chapter 20, we'll be looking at ketones and aldehydes. We can see a carrot here, which contains beta-carotene, which is a compound. The structure here is beta-carotene, which can be synthesized from aldehydes or ketones. This is vitamin A, which can also be synthesized as well. Ketones and aldehydes are very common in biomolecules, and they're important in the synthesis of many medicinal compounds. And we'll see a lot of those concepts in the course, building on top of carbonyl. The carbonyl group is common in both ketones and aldehydes. Vanillin we're familiar with, which we reduced in one of the experiments already. We will see cinnamaldehyde in the lab. Carvone is the spearmint flavor, which contains ketone. We have benzaldehyde, which is almond flavor, and progesterone and testosterone, which are hormones. They both contain carbonyls. When we name aldehydes, we want to make sure the parent chain includes the carbonyl carbon. Aldehydes always have to be at carbon number 1. If this is butane, the aldehyde that corresponds to that would be butanal, where it has the al ending. The parent is octane here. But if I put an aldehyde on the group here, my longest chain has to contain that aldehyde. This would be 2-propyl hexanal. The aldehyde will always be carbon 1. This would be 5-hydroxy, 5,6-dimethyl, 6-heptene-al. So the ene tells us there's an alkene there at carbon 6, and we have the al is number 1. This would be the correct numbering. This would not be correct numbering. This would be 7-hydroxy, 3-propyl, 4-heptene-al. For ketones, if this was butane, the ketone gets the -one ending, so this becomes butanone. More specifically, this would be 2-butanone because that's where the carbonyl is. We will never see a carbonyl at carbon 1. That would make it the aldehyde. This here would be 3-heptanone or heptane 3-one, which is the less popular version. This is 2-methyl cyclohexanone, 6,6-dimethyl 2-heptanone. This is a summary of reactions that we've used previously to make ketones and aldehydes. We have oxidation of a primary alcohol using PCC to get the aldehyde. If we do ozonolysis under reductive conditions with DMS of an alkene, we get 2 aldehydes. Hydroboration of an alkyne will give us an aldehyde. To get ketones, we have an alcohol that is oxidized using a Jones reagent. If you have ozonolysis of a tetrasubstituted alkene, we'll get ketones. Acid catalyzed hydration of an alkyne and a Friedel-Crafts reaction can also get us a ketone. So what makes the carbonyl a good electrophile? It has resonance, which we can see shown here. There's induction, and also sterics help to play a role in it being a good electrophile. If we're looking at these carbonyls below, which one is acting as a better electrophile? The aldehyde is better. There's less sterics here. When performing a nucleophilic attack, an aldehyde with I-, if the nucleophile is weak or if the attacking nucleophile is a good leaving group, the reverse reaction will dominate. So this is an aldehyde here. If the I- attacks as the nucleophile, this is the tetrahedral intermediate. And here there's a good leaving group, which is better than H. So if those electrons can reform the carbonyl and kick off the leaving group, it will. So we just get the aldehyde back. If you have a strong enough nucleophile and it's not a good leaving group, you will get the full addition. and form that tetrahedral intermediate. There's no good leaving groups here. There are no good leaving groups. So we'll get a proton transfer. If the nucleophile is not good, what we can do is make the carbonyl a better electrophile. So you can add acid. This will do a proton transfer. Then you add your nucleophile. And there now is your product. So by protonating this increases the electrophilicity 1 times 10 to the 6. But is there a reason why the acid is not used with strong nucleophiles? So this would get protonated. So not only could the acid protonate the carbonyl, the acid could also protonate the nucleophile. Water can be used as a nucleophile in these reactions. If you have a ketone plus water, you could form the diol, but the equilibrium favors the acetone as opposed to this diol. If you have formaldehyde, this is actually preferred greater than 99.9%. And if you add electron withdrawing fluorines on there, most of the compound will be in this form. This is greater than 99.99%. So how does this happen? Well, the nucleophile of the OH minus under basic conditions with water can attack here, so this is basic. So we get the anion of the O minus, and there's usually water present, which can do a proton transfer. And then we have the two OHs here. This product can also be made under acidic conditions. We get a proton transfer. The water that was created here can then do an attack. We have that positive charge, and another molecule of water can pick up that extra proton. To get the same hydrate. Instead of having water act as a nucleophile, we can also use an alcohol. In this case, the mechanism is similar. We first grab a proton from the acid. These steps will all be reversible. The alcohol is now acting as the nucleophile. That will attack here. And all that stuff comes along. So this is protonated. We're going to get a proton transfer here. So this proton here is going to get transferred over to this position. have a good leaving group of water. So my carbonyl can reform even with that R group there. So these electrons will come down, kick off the water. So I've lost water. I have OR, and that's positively charged. There's another equivalent of alcohol floating around. So there was 2 ROH. So that can attack here. Get a proton transfer to pick up this H. This is an acetal. We also get water as a side product. So an acetal is a carbon that contains 2 OR groups. So when you're trying to come up with what acetal is formed, you have 2 ethanol here, and it's going to attack this aldehyde. So what you can do is think of splitting this down here in the middle, and then kind of peeling those apart. So I redraw my carbon chain, which is just the 1 carbon. I have 2 ethanols that need to get added, or 2 ethoxy, and then OET. So you can think of taking a scissors and cutting this in half, and those break up into the 2 bonds, and then you put the 2 OETs on top. The same thing can happen with the carbonyl or the ketone. And just think of slicing this in half. OET. OET. If you have this ketone here, that's the same thing's going to happen. But now these alcohols are attached to each other. There's 2 alcohols within the same compound. So the first one attaches, and the second one does as well. We get a cyclic acetal. Acetals can be put on and taken off pretty easily. To put it on, you have the alcohol, or the diol in this case. You lose the water in the presence of acid. And if you add acid and water, that will remove the acetal. If you actually go back to this mechanism, you can draw all of these mechanism arrows in the backwards direction, and that will get you from the acetal into the water. So we put water into the reaction to get the acetal. In the backwards direction, you have acid plus water to get you back to the ketone. Because these are easy to put on and take off, we can use an acetal to protect aldehydes or ketones so they don't react in the presence of other electrophiles. If you had an ester that you wanted to reduce, we know that we need to use lithium aluminum hydride, but if you use lithium aluminum hydride, that's going to reduce. This is going to reduce the ketone to the alcohol as well as the ester to the alcohol. But if you want to keep the ketone intact here, then we can protect it using acetal. With acid, and it doesn't need to be a cyclic acetal. You can use the ethoxy or a methoxy. You get this. Ester is still here. You cannot form acetals with esters or carboxylic acids. And then here you would do your lithium aluminum hydride. Excess for the ester. This is still here. You've reduced the alcohol here, and then you just need H plus and water in order to reform the carbonyl. So in this reaction, if you have the diol, what reagent is here? We have a carbonyl and a cyclic ester, or a lactone. This will protect the aldehyde. So I'm just going to draw this down here. We get that, and then we need to add excess LaH4 plus water, and that will open up or reduce this. When you add acid plus water, the acetal will convert back to the aldehyde, and the aldehyde that is present will then react with the alcohols forming a new acetal.